Now, we've already introduced the notion of tautology and the notion of tautological consequence for dealing with our truth functional connectors. And there are similar notions that we can define for our quantified sentences, and this is going to be what we do in this video, namely to identify a notion that corresponds with tautology, which we call FO validity, and a notion which corresponds with tautological consequence, which we just call FO consequence. At the outset of this course, we began with three general notions that we wanted to formalize for the sake of our propositional logic. These are the notions of logical truth, logical consequence, and logical equivalence. And in our propositional logic, these are roughly equivalent with the notions that we developed of tautology, tautological consequence, and tautological equivalence, which we proved with truth tables. But now, we are into new territory with first-order logic, and we need corresponding notions for these three basic logical ideas that we've put into our propositional logic. The first of these, which we'll be discussing in this video, is validity. The second is first-order consequence, and the third is first-order equivalence. The present video is going to deal with these first two, and we'll deal with first-order equivalence in the next video. The first order of business, then, is an apology for this notion here of validity. Validity corresponds with the propositional logical notion of tautology, which corresponds with the general notion of logical truth. But we've also seen validity in the context in which it's used to describe arguments in which the premises can't be true without the conclusions also being true. Unfortunately, there's just this convention around using the term validity to describe the first order notion of what's roughly equivalent with tautology. We'll see some examples of these, but it just has to be borne in mind that FO validity is not the same thing as the validity of an argument. So we just have this equivocal term, validity, and we need to be clear that there are two kinds of validity being discussed here. In a way, a bit like what happened with soundness of deductive systems, which, as we saw in an earlier video, is not the same as soundness of an argument. So validity in this video is the first-order logical notion, which roughly corresponds to the tautology of propositional logic, and that just needs to be borne in mind. So let's turn to this validity now. So suppose we have a handful of sentences and we want to know whether they are FO valid. The way that we do this is to create translations of them, replacing all the predicates besides equals with nonsense or other predicates and see whether it holds. So we produce these translations. Let's go down the line. Everything is the same shape as itself. That's got to be correct, but is it FO valid? So we make this into a translation. I'm going to just make this little arrow with a T over it to be our translation into every X toves itself. Again, this predicate tove is meaningless. Well, that's by no means obvious that everything should bear this tove relation to itself. So this is not FO valid. Moving down to our next translation, we have, if everything is a dog, then Sparky is a dog. We know that our constants, like Sparky, have to name existing things, and we also know that our domain is non-empty, so it looks like this might come out as a logical truth. But let's try our translation using meaningless predicates. We'll just use a letter like R, and we'll replace Sparky with the constant A, and there you have it. If everything's in R, then A, which names an object in our domain, must also be in R. So this is FO valid. Moving on to our third sentence, let's replace the predicate cat with the meaningless predicate H. So this says A is an H and A equals B implies that B is an H. Well, recall again that we're not replacing the special predicate equals. And so this comes out as FO valid as well, because it clearly follows that if A is an H and A equals B, then B is an H no matter what the predicate H means. Finally, I'm going to write this translation of this big one down here. Bear in mind that this T arrow is just my way of showing that it's a translation. This is not a logical operator. Suppose we replace A as an icosahedron with T, and same shape with Z as a two-place predicate, then it doesn't follow that for any T here, if A is a T and A stands in the Z relation to B, then B is a T. So number 4 is not FO valid. If you like, you can even try coming up with some counterexamples to 1 and 4. Here's a way you could retranslate 1 using a meaningful predicate. You could say every X is taller than itself, which is obviously false. You can do the same for a sentence like 4 down here. So if you'd like, I'd encourage you to pause the video and think about how you would come up with your own retranslation of for, which is obviously false and thereby reveals that for is not FO valid. Here's one such example that you could have given, although there are many that you could give that show that for is not FO valid. A is a cube and A and B are in the same row implies that B is a cube. It's easy to see that this could be rendered false, and so this translation also serves as a counterexample to it. So a first-order sentence is FO valid if it is a logical truth when you ignore the meanings of all of its names and predicates as well as function symbols, although we're not looking at function symbols in this course, other than the identity symbol or equals. We keep that intact. And recall from our earlier video that if we encounter does not equals, we'll translate this into equals plus negation, because A does not equal B is the same as the negation of the identity A equals B. That then gets us our notion of FO validity. That's the first part of this video. The second part is first order consequence here. So let's look at how that works now. The notion of first order consequence is basically like the notion of first order validity in the sense that what we do is we take an argument and we replace all the predicates and names with meaningless ones or gibberish ones to see whether validity is preserved. So for instance, consider the following argument. Everything is such that if it's a dog, then it's not a cat, and Felix is a cat. These are our premises. And from these we can derive Felix is not a dog. But is this an FO consequence? Well, let's try translating it. This first premise translates to, for every x, if it's r, then it's not h. And the second will translate as a is an h. And so from this, it quite obviously follows that a is not an r. And this argument is valid. The point then is that we've translated this without paying any respect to the meanings of the names of the predicates to produce another valid argument, and that's what FO consequence is. So that's how we can prove FO consequence. And we can prove that FO consequence doesn't hold by constructing a first order counterexample, which is what we're going to look at down here. So consider what the following premises say. The first tells us that there isn't anything smaller than A, and the second tells us that B isn't smaller than anything else. Now, this could be true in a setup in which the only two objects are A and B and they're the same size. But this third premise tells us that there is something smaller than something else, and so in order to say that there's nothing smaller than A, it has to be that C, although smaller than D, is not smaller than A. And since B is not smaller than anything, as our second premise tells us, although C is smaller than D, which means that D is larger than C, it can't be that B is smaller than D. There's difference of size here, and as a result, there must be the case that A is smaller than B, at least on the way that we've set this up. But this is not a first order consequence, and we can discover this by translating this, giving meaningful terms in which the premises hold and the conclusion does not. So here's a counterexample. So let's try translating this one predicate that we have, smaller, to another predicate, friend of. So nothing is a friend of A, and B is a friend of nobody. This is what our second premise says. And C is friends with D, or a friend of D. Well, this just doesn't work. In fact, if you take this predicate friend of to be symmetrical in the sense that friend of AB is equivalent with friend of BA, since for anything, if I'm a friend of it, it's a friend of me, well then, suppose that nothing is friends with A, so the first holds, B is friends with no one, so the second holds, C is friend of D, totally different, and then it does not follow that A is a friend of B. So we have a counterexample here, a first order counterexample, which tells us that although this argument on the left-hand side over here does look valid, it doesn't survive these translation instances, where we replace the predicates and even the names to come up with these counterexamples. Now, all of this suggests a more general notion of a kind of replacement method, and we're going to conclude by looking at this. To test for first-order validity for sentences or first-order consequence for arguments, replace all the names and predicates and function symbols, if there are any, except equals with new, meaningless ones, and see if it holds. For first-order validity, take a sentence and try coming up with a meaningful interpretation, a reinterpretation that is, of the names, predicates, and function symbols in which the sentence in question is false. If there are none, then the sentence is FO valid. As for FO consequence, we do something similar. For FO consequence, we likewise reinterpret the predicates, names, and function symbols in the premises and conclusion to see if there's a way things can be that renders the premises true, but the conclusion false. And if there isn't any such, then the argument is an FO consequence. Now here are two concluding remarks. The first is that, quite obviously, for this way of showing FO validity and FO consequence, there's a good deal that's left up to our own judgment and ability to come up with a counterexample. So we say if there are no interpretations which render it false or invalid, then it's valid or it's a consequence, a first-order validity or a first-order consequence. But that doesn't mean that there isn't a counterexample out there that we haven't come up with yet. So we're kind of relying on our own ingenuity here in a way that we weren't to show these things with truth tables where we just straightforwardly, mechanically drop them in to see whether the T's and F's lined up in the way that we wanted them to. The second remark is that the tautologies will themselves be FO valid, but not the other way around. And the FO valid sentences will be logical truths, but not the other way around. So we can represent them with a Venn diagram like the following. At the center, we have our tautologies, like P or not P. Then, larger than and not contained in that, we have our FO validities. For example, if everything is an R, then A is an R. And larger still than that, we have our logical truths, such as A is equal to B if and only if B is equal to A. So it's important to keep in mind these different notions where all the tautologies are FO validities, but not the other way around, and all the FO validities are logical truths, but not the other way around. FO validities don't catch all the logical truths, and tautologies don't catch all the FO validities. And the same will hold, of course, for consequence, at least in terms of how these stack up in terms of tautological consequence, FO consequence, and then logical consequence.